So yeah, we can run through a couple of these design features. Let's go and have a look at. First of all, let's have a look at the 7-day cooldown period. Okay, so the mechanism, like the liquidity protection mechanism that was on before June, was previously treated as or modeled as, I should say, an at-the-money American perpetual option. You can go back over the V2.1 economics by paper to understand where that came from. But essentially, there is a type of arbitrage that we don't necessarily know whether or not it's even possible to perform it, but it exists in the math. And so the way that the system is designed, and we can have a look at this chart here, is basically that there is a time period where for a certain volatility profile and a certain revenue potential for any two assets in a pair, you can show that because the fees accrue in linear space, but the IL accrues only in as the square root of that same time frame, then there is a time where you can be fairly confident that the linear accrual fees is going to outpace essentially the costs of setting up that pair. And so this is the work that really formed the foundation for the insurance model. And it's really not there's nothing wrong with it. It's really just that the volatility and things for certain token pairs can obviously change over time. And it also doesn't take into account sort of crowd psychology and other things. So it's a purely mathematical model. But essentially, based on these results, we sort of estimated whether or not this arbitrage opportunity existed after a certain length of time, and came to the conclusion that after 7 days, it basically starts to look pretty flat, and therefore we could bring the cooldown from what was 100 days in version 2.1 down to about 7 days, and be essentially no worse for wear. And we never really had an opportunity to examine in a real life situation whether or not that would be true, because the protocol didn't offer insurance protection for very long. But this mathematical model is still something that I think is worth further research and certainly worth continued study. Okay, so when we get down to unstaking, which is in, I think, page 31 of the BIP15 documentation, we need to have a look at a couple of different things. So first, be aware that sort of 99% of the complexity of any of these DeFi protocols has to do with withdrawals. So when a user is withdrawing from the protocol, there are a couple of things that we need to check. The first is obviously, under the liquidity protection paradigm, what the user's staked value is actually worth. And then we have to perform a calculation to determine how many tokens are available for that balance. And if there's more tokens than are required for all of the liquidity providers' balances, this is called a state of surplus. And if there's fewer tokens than are required for all of the liquidity providers to withdraw, then this is called a state of deficit. And so we have a different conditional logic that handles both of these cases. But we also need to know whether or not we trust that state. We also have to calculate the value of BNT tokens compared to the token that the liquidity provider has provided and is asking to withdraw, so that when there's a liquidity protection payout, that the protocol issues them the correct number of BNT tokens. So there's a huge amount of complexity here, and in order to in order to do that, we've had to create some math that's never really been used in AMMs before. So the first part of this is to know about the cooldown period. So this cooldown period essentially keeps all of the positions fungible, which is one of the things that was built into Bancor version 3 because we wanted to focus on things like composability. And so while your tokens aren't in cooldown, they accumulate fees along with everyone else's pool tokens, which means that they grow in value over time. But when you commit them to the cooldown contract, the value of those tokens becomes fixed. So here we can have a look at this situation where a user has 1,000 pool tokens. This is the staking ledger, and this is the pool token supply. And so if we have a look at the pro rata share that this user is attempting to perform, we can see that he's got 1,000 of this 1,234,567 pool token supply. So we take that ratio and we multiply it by the amount of TKN that's committed to the staking ledger. And this staking ledger includes all of the tokens that have ever been contributed directly from users, and also all of the fees that have accumulated to that token over time. So when we take this number, the amount of pool tokens divided by the pool token supply multiplied by the staking ledger, we get some value. Let's just call that X. Now that X value is the amount that gets locked up, right? So this is the thing that this user will be committing to cool down. And this is the 7-day waiting period. When they get to the end of that cooling period, the idea is that they're given this option, right, either to cancel or confirm that operation. If they confirm the operation, this will be the amount that's withdrawn, and this number is passed to the rest of the withdrawal logic. Whereas if they cancel it, no harm is done, and the pool tokens that they committed to withdraw are simply returned to them. Now, what's interesting is that in this example, what I'm showing is that during that 7-day period, the value of these pool tokens can increase, right? They can never decrease under the design principles of V3 in a liquidity protected paradigm. So as the balance in the staking ledger has continued, this user, if they cancel, will actually be eligible to withdraw more TKN than they would have previously. Because if they just cancel this, then their pool tokens just go back to being regular pool tokens. And if we perform that same calculation a second time, we actually end up with a greater TKN balance than before. And this was meant to provide at least an opportunity for the user to second guess, right? If it's been an especially productive week and they want to instead withdraw the greater number of tokens that they would have accumulated, then they can cancel this process and begin it again. So this is kind of the basics. The other thing to realize here is that we introduced a second layer of conditional logic that was basically trying to give back the user all of their balance in TKN where possible, which basically assumes that even when they're receiving BNT as part of their liquidity protection, that they would generally swap that back on the pool immediately for more of the TKN that they first staked. So when during withdrawal, we take that assumption and we say, okay, if we already know that they're going to do that, then below a certain threshold, we can just have the protocol do that for them. And this will save them a step. It also means that the tax ramifications of that action is slightly reduced. And we basically drew, you can go, I should actually make some of the proofs for this public, but there's a surface where we have a look at the amount of TKN that's actually in the liquidity pool at any one time, plus the amount of TKN that's not in the curve at any one time. And there is this membrane that you can see in this z-axis that has a look at the maximum TKN withdrawal that can be supported using that methodology without creating an exploit opportunity. And so, we have to take this into account as well. I'm going to show you, what some of these look like in Excel before we hand it over to Mike to show us what it looks like in the simulator. But I do encourage you to go and have a look at these, have a look at some of these equations. But there will be, I will add a supporting document here that I never actually published, don't have the opportunity to publish, that goes into the derivation of all of these equations. But it's definitely the most complicated part of V3. And I'm going to show you right now on Excel how these things behave and what their function is. So let's do that. Okay. Is my worksheet showing up just now?
Yep, you're good.
Okay, yes. Great. Okay. So you can see that there are essentially 6 discrete possible outcomes here. So there's a logic, a conditional logic tree that can have one of 6 different outcomes. There are 3 for surplus, and there are 3 for deficit. So let's have a look at surplus first. So these are all, each one of these columns is obviously a different component within the system. We can set up, pool balances here. The TKN excess, you can think of as being like the off-curve component. So it doesn't mean TKN surplus, it just means the amount of tokens that I'm currently committed to the curve. The staked amount is obviously the balance on the staking ledger. And the, this part here is what the user, these are essentially the user inputs and outputs. So let's have a look at an example. I'm just going to change these around to slightly larger numbers. So let's say that we've got an off-curve and an on-curve component that are equal, so 1,000 each. And then let's say that the staking ledger says that there should only be 1,800 TKN in the system. So this is a surplus situation. So, if all of the users in the system wanted to withdraw all of their TKN at once, the system would only lose 1,800 of them. But you can see that the total balance of TKN in the system is actually 2,000. So there's a surplus of TKN equal to 200. Now we've got a user here that is trying to withdraw 10. You can see I've got this TKN expected result, and that this is denominated with the letter X. This is that saved amount that was a part of the saved value of the pool tokens that they're withdrawing from during the cooldown period, right? So this X letter here that I've included on my table is not incidental. It's actually the same X value that is described in the bit15 documentation. Okay, so from these 10 TKN that he is attempting to withdraw, we of course also had an exit fee, and this exit fee is actually critical to powering this this automatic mechanism where the protocol would sort of self-heal itself and also allow the user to withdraw entirely in the TKN that they wanted, again, when the liquidity protection paradigm was running. So if we have a look at what happens when I change that number, let's say I change this to 0.0015, you can see the amount of TKN that they're receiving after the withdrawal is also slightly different. Now, I should point out that since the liquidity protection has been paused, I think the exit fee has been reduced to 0, and there is also no cooldown period at the moment. But these were critical to prevent abuse and exploits while those features were up and running. So let's assume an exit fee of 0.25% for now. And that means that of the 10 TKN that they were trying to withdraw, the system is obligated to return 9.975 of those. So let's have a look at how that 9.975 is actually withdrawn. There are a couple of things here that I want to bring your attention to. One is that at the beginning and the end of this macro process, we want the trading liquidity inside the pool to essentially be completely unchanged. We want, obviously, the price of the BNT and the TKN to be the same. And we want to keep the overall state of surplus or deficit consistent. So that means that if there's a pool in deficit, users that are withdrawing from the protocol ahead of others aren't injuring the users that are remaining in the protocol behind them. And similarly, if there's a state of surplus, we don't want users who are exiting the protocol late or something to get an unfair advantage over users who left the protocol early, something like that, right? We want everyone to be held only to the conditions of the protocol at the time that they choose to withdraw. So what's interesting here is that if you're in a state of surplus, so we've got 200 extra tokens that don't really belong to anyone. This gives the protocol an opportunity to use those tokens to perform other activities. So, for example, you'll see here that even though 9.975 tokens are being withdrawn, the trading liquidity on TKN actually increased as a result of this withdrawal. So the TKN trading liquidity went from 1,000 to 1,001. So that's interesting, right? Even though users performing the withdrawal, the trading liquidity is actually increasing a little bit. But you can see that increase is more than offset by the amount of off-curve TKN that the protocol has access to. And in fact, if you have a look at these two numbers, right? So this this 11 minus this one here, we should get the exact number of tokens that the user is receiving. Okay, so let's have a look at this. What's really happened here is that these 11 tokens that came out of the off curve, 1.1361 of them were put on curve, and the other 9.975 of them were returned back to the user. So in this sense, this withdrawal is already complete from the user's perspective, but then we should have a look at what happened over here. We started with 1,000, 1,000 on the curve, but during the withdrawal, the protocol removed 1.137096 BNT from the curve and added 1.1361 TKN to the curve. What this has done is slightly change the price between BNT and TKN, okay? And it changed the price to the precise amount that if an arbitrager was watching and they saw that opportunity get created, they would be able to close that arbitrage by exactly adjusting the liquidity balances back to the point that they were before this withdrawal was processed. And so this is the interesting component, right? This is why we need to be so careful, is that obviously this is going to be a very attractive component of the system to attack. And so what we needed to make sure is that there are no that there's like a threshold that we set such that this arbitrage value that is essentially being paid to the market has no profit motive if you actually are someone who's withdrawing from the protocol. And this is actually what the exit fee was always for. And if you read very carefully through the documentation, I pointed out that it's actually not a revenue source at all for the protocol. It's actually kind of a cost, like it's a literal running cost of the protection mechanism, which is also why it was fine to set it to 0% when the liquidity protection mechanism was turned off. So let's assume, but let's just have a look at exactly how this works, right? And I'm going to show you what these numbers, Hmax and Hlim, eventually sort of collapse on. if we have a look at how valuable this arbitrage opportunity actually is, right? And I can show you, there are arbitrage equations that we can go through maybe another time. But you can basically reverse engineer these numbers in order to set up this arbitrage position the way that you need it. So just take me at my word for now that those conditions have been calculated here. What we're really trying to do now is work out what is the value, right, of that arbitrage condition. How much value can be taken by an arbitrager after this thing has been set up. So if we have a look at this difference, okay, the amount of BNT here that had to be paid in, okay, was this minus this, which, sorry, my mistake, should be this number minus this number. There we are. Okay, so 1.13 BNT is obviously equal to this number up here. Just trying to show you where this is coming from. And then we have to look at the amount of TKN that the arbitrager extracted, which should be this number minus this number. Okay, and again, it's equal to this white number up here. So if this is the BNT paid by the arbitrager, and this is the TKN bought by the arbitrager, and we know that at the time the withdrawal was processed, that the BNT and TKN rate was 1-to-1, then the difference between these numbers is essentially the arbitrageur's profit margin. And so in this case, the size of that arbitrage is actually negative, right? There would be no advantage, I think. Yeah, so there's no advantage performing this arbitrage opportunity as it is. But what if the user was withdrawing a slightly higher number? Okay, let's say 100 TKN is the amount that they were withdrawing. Now this arbitrage opportunity is actually starting to look pretty good, right? So there are about 0.1 worth of tokens, right, measured in BNC or TKN that they can potentially close this arbitrage opportunity for. And as a as a percentage of the amount that they provided, right, it's almost 1%, right? So it's not a trivial arbitrage opportunity. This is like sort of middle of the course, right? About average, I guess, for an arbitrage opportunity that would actually entice someone to act after gas. Okay, so this is 0.93. Okay, let's convert these into TKN units. Okay, so we know that these are actually equal. So this number here is let's call it the effective number of TKN taken by the ARB. Okay, this is after this process is completed. Now what we want to do is we want to compare that number to the effective number of TKN that was paid by the liquidity provider as they were withdrawing. And we know that number is going to be equal to the amount that they were expecting to withdraw minus the amount that they actually withdrew due to the withdrawal fee, right? So this is kind of the withdrawal fee in TKN. Okay. And now what we want to do is compare these two numbers, right? As long as the withdrawal fee in TKN is higher than the effective arbitrage, in this case it is 0.105, then there is no exploit, right? And what I mean by that is we need to assume that the person who is performing the withdrawal and causing this arbitrage situation to rise is also the arbitrager, right? And if they're not, someone will eventually create a smart contract system to perform this in an automatic way and just abuse the protocol forever. So we need to make sure that the cost of the withdrawal is always higher than the arbitrage. How do we know what that is? If we look up here to Hmax, this is essentially the precise withdrawal value where the arbitrage value of this of this setup becomes greater than the withdrawal fee, and I can show you that now. So if I just let, for example, this X value be equal to H max, you should see that the effective number of TKN taken by the arb becomes exactly equal to the withdrawal fee in TKN. And any number over this, right? So if I just let X be, say, 217, so if I go over by even one token, now the number of tokens taken by the arb is actually higher than the withdrawal fee. Okay, so that's what this Hmax profile is. So that's how the mechanism operates for the system when the liquidity protection is switched on, and these are like viable parameters inside the system. And so what I'm trying to demonstrate here, we can kind of go into, probably this is too much for a single session, but we can also go into how deficit is handled, which is the exact opposite. This has to do with arbitrage opportunities between BNT and TKN, rather than TKN and BNT. And we can also have a look at how some of these other components are other parts of the decision tree are handled. So yeah, as I said last week, I think that the withdrawal logic is probably far too much for a single for a single sitting. It's probably it's the single most complicated part of version 3, and so that was 1/6 of the 1/6 of that logic tree that we should explore. And yeah, I think I'll drop in the simulated chat a PDF that explains how to derive some of these formulas, and I think that will serve as a good supplement to studying the simulator. But I think I'm going to stop my explanation here because I can see we're already over time, even though we only got through that tiny little part of it, so that Mike can show what the withdrawal looks like. But just think, while he's going over that part, what it would mean if someone performed a swap immediately before they executed their own withdrawal, right? You could essentially change the price of your TKN to be anything you wanted. And so this is why the EMA is used, to make sure that the internal price of the token inside the protocol is stable before the protocol sort of allows that withdrawal to continue. And this is a very important prevention for abuse and hacks and other things. So I think I'm going to I'll stop there, and in the over the next 10 minutes I'll let Mike show us what a withdrawal looks like in the simulator. But I think we should probably continue this discussion on withdrawals into the next call. But Mike, go ahead.
Great. Yeah, I think that we're kind of adjusting some of the original 9 sessions that we announced, so we can, Jen, if you're listening, maybe update that. We're already gonna plan for a couple more. So like last week on the EMA was not really in the schedule, and then we're splitting the withdrawals, which was originally kind of just noted down for one of these sessions, but quite obviously it's going to take a couple of them. So nevertheless, today we're looking at a new notebook that I created for the purposes of the withdrawal discussion. This one is part 4 of 4. I'm going to go ahead and edit that to 4 of 6 or 8 or whatever we end up doing here. But once we get off the call, I'll push this up to the repo, and you're welcome to have a look and run it for yourself. Same thing that we've done, in previous sessions, just to get the system set up in the way that we want it. You'll notice here that for today's discussion, I've added a new parameter into the Bancor DApp initialization class. This should be a cooldown time, which is going to be in days, and you can adjust that and play around with it as desired. We just keeping in like a consistent pattern from the last couple of times. This is really the same process that we've gone through, creating the users, doing some deposits. Here we're checking the network fee, just based on some previous discussions around that, displaying the network fee. We're doing, again, we're doing some deposits, enabling trading, iterating the timestamp, and then doing some trades after that as well. So eventually you'll get down to here where we say begin withdrawals, and just playing around with this, shortly before we started the call today, I was going through the motions of doing a withdrawal and noticing just some odd behavior, like the balances were not coming back, and I was, a bit perplexed. Just anyway, it turns out that's why I put this first and foremost here, just in case you run into the same issues. It should be pretty obvious in hindsight, and especially if you're following along with these sessions. Mark, the last thing that he touched on there was this point where the EMA check and the price stability internally is one of the conditions which allows the withdrawal to be processed correctly. And if that condition is not met, of course, it's not going to process correctly, in which case you might be running withdrawals and not seeing it do anything and wondering why. So here, I'm just kind of showing so that the cooldown time that we've set, and I'm not sure, I might run this all again, restart and run all cells. And so we've got the price is stable equals false, basically, at this point, right? And in the next step, just for the purposes of demonstration, and maybe, since we're going to be doing a couple calls now on the withdrawal process, perhaps for the next session, I'll go through actually processing, some trades and doing some deposits, and even configuring the price feed appropriately so that we end up at this point with like a stable price, basically, without having to like override things. But here you'll notice this one line, I'm just setting the spot rate equal to the EMA rate equal to the inverse EMA rate equal to the inverse spot rate, and then resetting the state. And then we can see now that the price is stable, we can go ahead and process the withdrawals and see the behavior that we were looking to demonstrate today. So, again, this is like one way that you can, you're quite obviously, if you're playing around with the simulator, you're going to want to know how to override certain things when you're just trying to figure out how it works. So if you need to override the price stability, this is like a quote unquote hack to accomplish that. And from that point, the way that the backender, let's call it the simulator state database, if you will, is tracking cooldowns by an ID number. So when you call begin cooldown, here and you've got some options here. You can call the pull down or the cooldown with a pool token amount, or with the reserve balance or the reserve token amount. So just be aware that there's some options there, and that's why it's PTKN. There's also an RTKN, which will do it just in different units. And so here you can see we put in the amount we want to withdraw, the token name that we want to withdraw, the user, and the timestamp. And then by just printing the pending withdrawals for Alice after we do that, you'll notice that we've basically are returned a dictionary within which we have an ID, which is set at 0 because it just starts iterating, pending withdrawals, right? So if over time, if we call it again, it'll iterate. This ID will become number 1, number 2, and so forth. So it logs the timestamp that the cooldown was created at, the user who created it, the token, whether or not the cooldown is complete and the withdrawal has been processed, or I should say whether the withdrawal is complete, and then we just call describe here to print the state. You can see that our ETH balance, we're withdrawing ETH. It's at 500,000 here. If you go up and look at here, it was at 500,000 as well. So we begin the cooldown, but no balances have actually changed yet. And again, if we do a withdrawal, we put in here the ID number of, that's what this is referencing, by the way. I had a couple of these up here, so maybe to make this more clear, I'm going to put this as the ID number. And here, I believe that what is happening is that, so we have a cooldown period or cooldown time setting right now of 7 days, and because our previous timestamp was only 3, our timestamp at this point is basically 4, which means that we've not met the cooldown period yet. Even though we're calling withdrawal, it's not going to actually return the tokens because we're not past the cooldown timestamp. However, if we do the same thing, and I'm going to again change this to the ID number here to make it more obvious what's happening, and we call withdrawal one more time, but this time we do the timestamp +7 just to be sure that we're past the cooldown time period. You can see that the ETH amount is returned to Alice's wallet, and minus the withdrawal fee and everything else. So we can then check one last thing that Alice's pending withdrawals, this is complete, is now set to true, which means that we can't basically double withdraw the amount. So that is kind of a quick run through how to operate the withdrawal method of the Bancor dApp class. Obviously, this is as Mark mentioned, there's a bunch of different types of scenarios. We didn't even get into here, demonstrating the different, checking whether we're in like a surplus or a deficit state, and or what's happening on the back end in terms of like those different conditions. Perhaps next time I'll set this up so that we can run through a bit more of what that looks like and how you can check the state of the system at different points in time. But we're going to call it a wrap for today and pick up again next session. Anything to add? Yeah, go ahead.
Yeah, just to bookend this, I'll just share my screen. I just added a document called Inside the Black Box, which basically walks through how this withdrawal algorithm works. It was never completed, right? So on page 21, there's basically no information, but there's still 20 pages of I think very very thorough notes. And so I basically derive I derive all of the withdrawal equations, starting with the really basic swap equations here. And these are all have appropriate footnotes, and everything is described in it's basically elaborated to the exact extent that you would have to in order to have these discussions with auditors, which is actually why this document exists and why it's only written up to the point where the discussions with our auditors were satisfied. So I originally had ambitions to improve on this and create a lot more sort of a lot more content for it. But I still think that it's worth sharing. It's got its own examples and things. And so if you are confused by anything that I've just said, and I'm sure that you don't feel bad. It's something that you wouldn't have ever come across before. It doesn't exist in any other AMM, so it's completely novel. But if you want to interrogate some of these equations for yourselves, I have added this PDF to our simulator chat in Discord. So feel free to grab it from there if you want it. And yeah, I think that's probably the best place to end it. And I think we should probably spend the next call doing a couple of other withdrawal situations before continuing.
Sounds good. Thank you, everybody.
Awesome. Thanks, guys.